Hi guys, it's Victor, and this is a solution for the problem Leetcode 5533. It's called minimum 1-bit operations to make integers 0. We rate the complexity of this problem as 4.5 out of 5 and its elegance as 3 out of 5. The problem is based on gray codes. Anyone familiar with the topic should be able to implement a solution easily. However, if you don't know the gray codes, you still have a chance to solve this problem within the limits by extending some observations discussed further on the bigger range of numbers. A sequence of binary numbers where two adjacent numbers differ in exactly 1 bit and every number has exactly one occurrence in the sequence is called gray code. There is an infinite number of gray codes, and these are pretty much reflections on a traditional binary code holding the invariant. As we can see from the problem statement, every transformation on the source number changes exactly 1 bit in the number. Luckily, the progression yielded by the problem statement has its specific name and is called the reflected binary code. You can read more about the reflected binary code, but we'll try to solve the problem naively by an observed regularity without producing all the theoretical foundation. Let's notice first that the problem is reversible. That is, like in Tenet, we can solve the opposite problem of transformations from 0 to our number. This solution will have exactly the same number of steps. Let's say we have the number 7. We can apply the progression of 5 transformations to get 0. And the same number can be produced from 0 with the same transformations reversed. So the solution for the opposite problem will be a number of transformations, which will also be an answer to the original problem. Second, let's try to build some big number up from 0 using the rules explained. Let's consider 2 to the power of 30, which is exactly 1 bit set on the 30th position in zero-base notation. In order to do so, we have to do the following. Set the 29th bit to 1, set the 30th bit to 1, reset the 29th bit to 0. Great! Now we have the question, how to set the 29th bit to 1? Well, by definition, the only optimal way without unnecessary operations of doing so is by setting the 28th bit to 1, setting the 29th bit to 1, and then resetting the 28th bit back to 0. So we see a similarity that can be generalized for a bit n. So to set the nth bit from 0, we have to set the n-1th bit to 1, set the nth bit to 1, and then reset the n-1th bit to 0. The first point can be achieved by the same recursive procedure. Now the question is how to reset the n-1th bit back to 0. It can be done in exactly the same way. That is, to reset the nth bit to 0, we have to set the n-1th bit to 1, reset the nth bit to 0, and then reset the n-1th bit back to 0. This progression of operations will be the most optimal by the problem definition. We can make an important observation here, that if we see our source number on the way to building some big number, the number of operations for our number to be converted to 0 will equal the position of this number in the progression of operations described. Please take a pause and think why. The explanation is if it was not so, we could have produced our big number by a fewer amount of operations using some shortcut. This contradicts to the conclusion that we are producing our big number by the smallest amount of transformations. The second important observation is that all the numbers less than 2 to the power of n will be met in the progression on the way to 2 to the power of n. You can pause the video and think again why. The explanation is if it was not so, we could have produced our big number by a fewer amount of operations using some shortcut. This contradicts to the conclusion that we are producing our big number by the smallest amount of transformations. The second important observation is that all the numbers less than 2 to the power of n will be met in the progression on the way to 2 to the power of n. You can pause the video and think again why. The answer is that on the way to setting the nth bit, the n-1th bit takes both values, 0, the source state, and 1, the required state to flick the nth bit. The same, to flick the n-1th bit, the n-2th bit takes 2 states, and so on. As our process is finite, all of the intermediate numbers are unique with no loops, and the amount of those intermediate steps is 2 to the power of n, which is the power of the set of all possible intermediate numbers. Now, let's build our way from 0 to 2 to the power of 30 and watch the progression in the hope to notice some patterns. We start with 0, and at that stage we can only flick the 0th bit. Now that the 0th bit is set to 1, we can flick it back to 0, or we can move further and apply the second rule. To move further and set the second bit in 0-base notation, from there we should reset the first bit. Any other allowed operation will only send us back down to 0. But we want to move further. So to move further and set the second bit in 0-base notation, from there we should reset the first bit. Any other allowed operation will only send us back down to 0 again. But we want to move up. By this moment we can notice that at every step there is only one way of producing a number that is not in our progression yet. So we simply follow the process. We see some pattern in the progression. This progression is the reflected binary code with its code A003188. You can search and read more about the progression. It's pretty logical at that stage to repeat this process and enumerate the steps. I remind here that if we get our source number in the progression, the position of that number in the list is the answer to the problem. By the way, the reflected progression also exists, and it's A006068. That is, the nth number in the progression is the answer for the source n. Now the key insight here is to represent the numbers in the progression with their binary code. Please take a few minutes and think if it's possible to come up with a way to quickly convert the numbers on the left to the numbers on the right. If you follow the digits from the greater to the lesser digit on a number on the left and its counterpart on the right, you may notice that all the digits on the right from ones are inverted. For example, if any digit from the first one is set to 1, it also inverts the lesser digits to the right from the second one. So, to transform the source number to the answer, we simply invert all the digits to the right for all of the source bits that are set to 1. Now that we have our solution crystallized, let's quickly look at the possible code. There are many ways to program the idea. We'll use a canonical gray code implementation. We start our iterator from the most meaningful digit and iterate down to the least significant bit. Next, we invert the immediate, less significant bit only if the current bit is set to 1. As we repeat this process for already modified bits as well, the transition passes through the entire number. The highlighted expression isolates only the less significant bit. But as a hard problem solver, you should be able to be familiar with this trick already. This is exactly the solution that was implemented by the user Izakina. Its complexity is logarithmic to the maximum source number. Please subscribe if you want to get an analysis of interesting programming problems, and let us know your thoughts in the comments section. Stay tuned, and goodbye.